Alright guys, today we will start off with a little XKCD. He's a hoot, and you guys will have some homework of another website that he does, his What If series. So that'll be a little bit of a fun diversion from just straight old calculations. I'll have plenty of questions for you guys to answer about that. That'll probably make it a little less fun, but at least it'll be kind of entertaining. So we all have thought about vanilla ice being one of the ices that could form, and you do anyway. So they have David Bowie and Queen singing "Under Pressure." Oh man, it's terrible. It's terrible. All right. So where are we? We are smack in the middle of chapter 8. And so what I want to do is I want to review homework. Then I want to lecture the rest of chapter 8. And in the next class, we'll review for our quiz and mostly begin chapter 9. I wanted to make sure we covered a bunch of the homework and really could get you guys prepared for that, and also have a work session, yes, on the 18th to answer a bunch of questions. Okay, so we will do that. That may actually mean we'll do not a whole lot of question answering on the 19th, because we will have just had a work session the day before. So y'all try to come to that. Make sure you're ready to go. I think we said 2 to 5, I think is what it was, on the 18th. So make sure you got that on your calendars if you have them, and in your brain if that's the only thing you rely on. Okay, so pull out your phase diagram homework here. And my printer, like maybe some of y'all's printers, is terrible, but maybe you were able to do it on a screen, and so had a little bit better detail that also was available. I should have told you, just Google it if you needed to, but it's in a higher res image than even I could get to you. All right, so let's roll through some of these. Make sure you've got all the right answers, because some of these will show up on a quiz. Okay, and of course we've got pressure going up this way, temperature going this way. We've got Celsius here, Kelvin here, bars here, and pascals, and all the kilo, mega, giga, pascals there. Okay. All right, so let's look through this right here. What's the definition of a triple point? The only thing you really need to know is that's right here, and that is the only point at which all three phases can exist at a certain temperature and pressure all at the same time. There is no other place. Anywhere on any of these lines, two of them can exist. Okay, two of them can exist at a time, because they'll be transitioning one from the other, and they don't just poof do that. So they'll coexist right there along here, but only here do all three of them exist. Okay. All right. What is each increment on the x-axis? 50 degrees C. Okay. And if you answered 50K, they start in different places, but they are the same increment. So either one of those would be fine. In fact, I did not even really look up here until just a little while ago. So either one of those is fine. The increments are, we talked in Celsius just because that's mostly where we're used to using things with water. All right, what's each increment on the y-axis represent? And we could have said a log 1 or 10 times the previous measurement. Okay, and we'll talk about this in just a second. It's called a log-lin plot. Why is that? Because it stands for logarithmic linear. This one is linear, which means it's just 50, 50, 50, 50, 50. This one is logarithmic. Okay, and of course it's got this kind of weird pattern where each increment is smaller than the last until they get pretty squished up right here, and you got 10 of them. Okay, and that's logarithmic. We go from 1 Pascal to 10 to 100. So what's this difference? This is only 9 pascals. Okay, this is 90 pascals. And what's this? 900 pascals. Okay, 9,000 pascals, and so on. Okay, so even though they look the same, they're getting much, much bigger, and that's useful for a whole host of calculations and representations. It's much better to represent the stock market over time this way because it's always compounding. We're always talking about growth as a percentage of the whole. Anyway, and obviously this is good to do. Otherwise, all this stuff would be squished up in a way that would not be very helpful. Okay, all right. And so what is atmospheric pressure in kPa? That was to just get you to kind of look at it or either look that up in your book or whatever. But we see that 1 atmosphere is right here. And we know that that's 101.35 kPa. Excuse me, 325 kPa. And to go from kPa to PA, we could write it like this if we wanted to. kPa. All right, and what is 1 kPa to make that cancel out? Well, it's 1,000 PA. Okay, and then you know you multiply by 1,000. Boom, boom, boom. There's our decimal at the end. Okay, and what is a bar? A bar, 1 bar is 1 atmosphere. Okay, so those clearly evolved at the same time, or this was, kind of an older measurement before Pascal's was around. You can see kind of by the random number 101.325 kPa. Obviously, that Pascal is based on something other than what we see around us. And so that was brought into line with all the other SI units. All right, pushing on very quickly here. All right, so this was to get you to think about the phase changes. Okay, so what's our first one? Keep it at 100 PA. Oh, and just we're at that. Okay, so we're at 100 PA. Okay, and 0 Celsius. Okay, so you just got to look and see which realm you're in. You're in the vapor realm. So hello, hello. That's how the British people spell it. So that's how we're going to spell it today. Vapor. Okay. Easy, easy, easy thing to get right there. Okay. 100 bar and 100 C. All right, where are we? 100 bar and 100 C. Okay, so that's just liquid because we're in this liquid realm. Super straightforward. Now this one's a little weird. 10 MPa and 400 C. So 400 C is boom over here. And 10 MPa is up here. Okay, so we're beyond, what do we call that? The critical point. So it's a supercritical fluid. That's you can see that a little bit more clearly in your book. But that whole area past that critical point is where it's a supercritical fluid. Okay, and these are the answers that I would expect you to give on a quiz. Okay, so there's no wiggle room, other words, something else we'd call it. No, these are the answers here. Okay, 1 PA and 0. We go to 0, which would normally in our 1 atmosphere would be a freezing point. Okay, but we're way down here with low pressure, and it's actually a vapor at that point. All right, and so that is, you've probably heard of, if you just threw liquid water into space, it would immediately boil off, and that's why, because the pressure's not there to hold those molecules together. They have enough energy, even at 0 degrees C, to turn into a vapor immediately, and I believe they would even sublime. I don't think they would even go through another phase. All right, right here, just conversions. 60 gigapascals. I hope everyone looked it up in Wikipedia because it really is kind of cool. 60 gigapascals. You need to know what giga is, and that's 1 times 10 to the 9th, or 1 billion pascals. Set it up like that. That's your answer. Proper scientific notation. Okay. And y'all be correcting these if you have them wrong, okay? And the same for converting to atmospheres. We take our pascals. 101,350 pascals is 1 atmosphere. We put it in our calculator, and that's what comes out there to atmospheres. This would squish you a lot, okay? You'd be dead instantly, of course. Number 8, as boiling point, describe boiling point as pressure increases. So what happens as pressure goes up? It uniformly increases. Okay, so the boiling point is this area between liquid and vapor. Okay, so technically it's not boiling down here past that triple point. So we would just be looking right here, but we could say just simply it increases. Okay, pretty straightforward, looking at trends on a graph. Okay, so if we go to Denver, lower the pressure because we're higher up in the mountains. Let's just say it's, what do we say? Oh, 82 kPa. You'd kind of come here and you'd come down 2 lines. So we'd probably be right about here and come across. And what's that? Kind of come down then. That's like 92, 95, somewhere in there. 90. So it's hard to tell with this poor of a graph. But the point is, it's less than 100. Okay? So we would say less than 100 degrees C. So if that's the hottest water can get at 90 degrees, you actually can't boil things as fast. Okay? So you're only heating potatoes or pasta or whatever to 90 degrees C. They don't cook nearly as quickly as they do at 100 degrees C. I think it's every 10 degrees increases the chemical reaction time by like 4 times. So raise it 10 degrees, something's 4 times faster. Raise it another 10 degrees, another 4 times faster. So that's pretty crazy. But that's why a pressure cooker works. So if we raise that to 200 kPa, we'd look at our chart and we'd see that the boiling point would be 110 to 115. Whereas 200 kPa, just this first line up here, boom, we hit right there. What's that? We'd say that's 110, 115. Okay? All right, what action is taking place if you hold, excuse my typo there, pressure steady at 10 pascals and raise the temperature from negative 100 to 0. Okay, so we're at 10 pascals and we're coming across. So we're going from negative 100 to 0. So what is that? It's going from solid to vapor, which we call sublimation. Okay. What about 100 PA and lowering the temp from 10 to negative 60? Okay, so we're at 100 PA, and we're going to move from 10 to negative 60. Again, we're going back across this line right here between solid and vapor, but now we are going the opposite direction, so that's deposition. Okay, go straight from gas to solid. All right, in 1 atmosphere, moving from 100 to 101. Okay, so at 100, it's boiling, and 101, it is all vapor. If that water is 101 degrees C, it is vapor. So that is vaporization. Okay, we're going to talk a little bit more about the difference between that and evaporation. Okay, they're both to change from liquid to gas, but they happen a little differently. Okay. All right, make those corrections if need be. All right, let's roll through the rest of Chapter 8 here. We're going to go through most of Chapter 8, and then we're going to work some examples. And then I hope you guys are going to be pretty solid on these. We can review a little bit at our work session on Monday. And so y'all bring questions, anything you weren't able to do, and tell me about that. Okay? All right, so let's talk about love. I'm just kidding. Let's not talk about love. Let's talk about heat capacity, heat diffusion, and heat of vaporization. All right. So basically, let's just get some definitions here. All right. If you take a solid substance at a temperature below its melting point and heat it, the added heat causes the substance to go through 5 different changes. Okay, so we're actually not going to start with definitions, excuse me. All right, temperature of the solid increases to the melting point 0. This is for water specifically here. Okay, and then we start at negative 20. So this would be ice. So if we put it on a flame, it would go to 0. Then it would melt, maintaining the temperature at the melting point as it does. Okay, now, of course, this isn't an ideal situation. If you were heating these, there would be some temperature gradients. Part of it would be liquid and then be warmer before all of it melted and all that stuff. But we're talking about if it all was perfectly distributed, the heat was perfectly distributed in that substance. That's what we're thinking through, okay? So as a liquid now, the temperature of the liquid begins at the melting point and increases steadily to the boiling point, which is 100 degrees C. Again, this is just for water. The substance vaporizes, which we were just talking about, maintaining the temperature at the boiling point as it does. Okay? As a vapor now, the temperature of the substance begins at the boiling point and increases. All right, so now let's just look right here and chart out what's going on. All right, so this is, again, water, but this holds true for any substance that exists at 3 different phases, which most of them do, which most of them do, okay? So we're talking about how much heat we're adding in here, and we're watching what the temperature does. So if we had this in a container and we were taking readings, what we would see is that it would start at -20 and would rise to 0. And even though we were blasting away with either a flame or an electric heater or something like that, that temperature would not change. Okay? So if we're adding heat and the temperature doesn't change, why is that happening? Okay? Well, what's happening is that heat, instead of going to cause those molecules to vibrate more, okay, and therefore raise their temperature, that energy goes into breaking the bonds apart. Okay? All right, and instead of causing that temperature to rise, it's breaking bonds, breaking bonds, breaking bonds. And once all those bonds are broken, now it can go into making the molecules vibrate more, which means raising the temperature. All right, so we're in a liquid here, we're in a solid right here, and we're in a combination of the two. We're in a transition period right here. So we're right on that phase diagram line and just hanging out right there. All right, so we go, boom. We raise up to 100 degrees, and this is where your water would be boiling. Okay, and again, that temperature distribution is why we have the difference between like a slow boil and a roiling boil, okay? Or bubbles that form versus an actual boil where that throughout the liquid molecules are being turned to and freed up and become gas molecules. Okay, so because the flame, let's say, is under the pot and the pot doesn't transfer all that heat immediately throughout the entire thing of water, there are parts of it that start to get to a vaporization temperature before others do. All right, but generally speaking, we stay at that vaporization temperature, 100 degrees C, this whole time. Okay, until every bit of it is gas. So if we were not cooking pasta and we were just kind of keeping everything around, like let's say this was in a steam turbine generator, okay, all that steam would still be in there. Well, we could continue to heat it, and it would just go up and up and up until we reach that critical point, and then things would get a little bit weird. Okay, so this is the characteristic shape of this graph: up, flat, up, flat, up. 1, 2, 3, 4, 5. Okay, they're all going to look like that. You will have a question about this. Okay? All right, so let's look then what we can do calculation-wise. All right, so what do we have right here? Oh, let me move it up a little bit. Okay, so what do we have right here? All right, we have Q, which is just the amount of heat. Okay, and what's that in? That's going to be in joules. Okay, then we have the molar heat capacity. Okay. Delta T represents the change in temperature. Delta, remember, means change anytime we see it. I'm sorry to be writing so small. I'm trying to fit it in my book here. So y'all just should be writing that in your book if you want to. Okay. And N is going to be the number of moles. Okay, so let's look very briefly at those units. What are we looking at? Okay, so we've got Q is equal to C in delta T. Okay, let me get focused here. Okay. All right, so what did I say? I said this was going to be in joules. And this is joules. The C is joules per mole degrees C. Joules per mole per degree C that it changes. Times N is just going to be moles because it's the number of moles. And then this is going to be degrees C. So what happens? Moles, moles, C, C. Good. Our units work. Okay? All right, so we're going to pack that away for just a minute, and then we're going to come back to it to actually work some problems. I just can't get past doing problems as the best way to understand what's going on in a situation. Okay? Okay. And so just to look at this right here, you can see what we've got going on. These are just empirical values, meaning values that have been found by experimentation. I'm sure they have gone back and theoretically proven these so that they all kind of make sense and link up. Okay, but so we've got a constant for ice, 0.0364 kilojoules per mole. And note that even though it's chemically the same, it's in a different structure. Okay, so that means it doesn't act the same way. And so see that it's kind of interesting that ice is actually very close to steam. Okay, and I think we would expect that because neither one of these has got those hydrogen bonds operating. Only water has those hydrogen bonds operating, and so it's going to be different. Okay, liquid water is always going to be different. All right, and so they've got double the amount here for water. Okay, and then this is the heat of fusion. Get used to this nomenclature here: heat of fusion and heat of vaporization. Okay. All right, and so that means for each mole of water that you turn from liquid to ice, you have to remove 6.01 kilojoules. Liquid to solid. Or solid to liquid, you got to add in 6.01 kilojoules. It's kind of your ticket for one way or the other. It doesn't matter. You've taken a mole one way to a solid or one way to a liquid. All right, and vaporization is the same. It's to go from a liquid to a gas. And again, look how much higher this is. That's amazing to me. It's almost, what is that? 7 times higher? 7 times higher to go from a liquid to a gas than it is to go from a liquid down to a solid. Okay? And so he has a note about the Q being negative. Okay, we always do final minus initial. Okay? No matter what you're doing, you're changing velocity, final velocity minus initial velocity. Changing temperature, final temperature minus initial temperature. Remember it, because I'm going to hammer you with it next year in physics, and the sooner you remember it, the better. Okay? It's super simple, and it will simplify so many mathematical problems that people have in physics with signs and even with just getting the right answer for things. Okay? So we'll go through some of these to make sure you guys understand them in just a minute. I want to make sure I cover all of the content here. Okay. Note that we've got a similar one here. What's missing? What's missing? Okay, so we had what? C in delta T. Well, that C is that specific molar heat capacity. We've got a heat of fusion, which is that same type of thing. Each mole takes a certain amount of energy, and that's the number of moles. But we're missing the temperature change. Why is that? Well, we look back here, And we look at as we're melting, this is the heat of fusion, even though it's going towards a liquid, we call it the heat of fusion. In the heat of vaporization right here, the temperature's not changing. Okay, that's the point. That's how we know that that energy is going into that change of matter, that change of state of matter. Okay, because there is no temperature difference. All right. And also, I just want to note that a calorie, okay, is the amount of energy to raise 1 gram of water 1 degree C, or 1 Kelvin. Okay. All right, and just in case you guys haven't heard it by now, a dietary calorie is different, and it's equal to 1 kilocalorie. Okay, so when you eat 3,000 calories, because you're young and your metabolism burns them all off, okay, you actually would be able to heat 3 million grams of water 1 degree C, or, you know, just doing the math there, you could do 30,100 degrees C grams of water. Okay? Just a note. Okay? Don't be confused by that. It's a good thing to know. All right, so let's look right here. Okay. Looking here at evaporation and what's going on here. Okay? Sorry to be all jerky there. All right? This did not ever seem all that complicated to me, but lots of books spend a lot of time on it. So basically, remember, you've got all these guys moving around in here. All right? And because in liquids, there's a random distribution of speeds, aka temperatures. Okay, this is true in gases, but it's also true in liquids, which is what he says right here. The distribution of speeds among the liquid molecules. It's slower, okay, but when you're at the surface right here, there are some of those molecules that end up being on this side of the distribution. So not very many, but some. Okay, let's say things turn to a gas when they've got 1,500 meters per second of a thing. All right, so any molecules that are so if they're inside the liquid, they're down in here, they've got extra kinetic energy immediately. Boom, they bump into another molecule and they lose some of that energy, and it gets distributed and spread back out. Okay, but if they're up here and they happen to be way up here, oh buddy, they're breaking free. They're at the escape velocity. They can get out of there. Okay, so that is evaporation. All right, you need to be able to explain evaporation. Okay, that would be a great narrative question that could be worth a number of points, because it's key to understanding what's going on a molecular level, why a liquid boiling is a fundamentally different thing than evaporation, even though they are both going from liquid to gas. Okay, but here's the interesting thing. Okay, we want to talk about evaporative cooling. So what happens if let's just say all the molecules eventually make their way to the surface here, and they've got this this distribution up here. Only these guys can escape. Okay. Well, if they all escape, this curve suddenly looks very different. Okay, because they've taken a lot of that kinetic energy with them. And he has the example here. Every time a graduating class of seniors leaves the school, so kids with the highest excuse me, kids with the highest age, as soon as they graduate, the average age of the students left behind drops because all the oldest students have left. Okay? So as all the high energy guys leave, they drop the average temperature in the remaining liquid. Okay? And so, anyway, we can still use that heat of vaporization because it still takes that amount of energy to get those guys from a liquid to a gas. Like you evaporate 1 mole of water into gas. That has absorbed or taken with it however many kilojoules. What's our specific heat here? Okay. Heat of it. So it's taken 40.7 kilojoules with it. Okay, so if you sweat and you evaporate 1 mole of water off of your skin, it's going to cool you by 40.7 kilojoules, which sounds like a lot. Okay? Well, it's pretty amazing because you have constant energy releasing oxidation in your body going on all the time. That's how you get energy. That's how you live. You're breaking down sugars and releasing those chemical energy in those bonds. All right, so for not only you to just have a bunch of heat in there, you're producing heat all the time. So for you to stay cool in an environment that is above, let's say it's 100 degrees, which happens all the time around here, okay? Your body is going to want to come to thermal equilibrium with that at 100 degrees. Well, we can't do it, okay? Our bodies don't work. I mentioned earlier that chemical reactions depend on temperature. Well, so many of our reactions inside of our body absolutely depend on a very specific temperature, like within tenths of a degree, okay? And what your body often is doing with a fever is trying to disrupt those chemical reactions in bad things, bacteria or viruses or whatever. Whether it works or not, I'm not exactly sure. But all that to say is the only way you've got to dump that heat is by evaporation, okay? Ultimately, even though they don't sweat, dogs do the same thing. Kangaroos, I'll send you a video of that. That's super cool too. They lick their arms, and then as it evaporates, it cools their stuff. So anyway, he kind of goes off on that as well too. I encourage you to read this. This is super cool too. All of this is pretty amazing. But basically, you need to know that evaporation takes heat with it. That heat of vaporization is still the same as if it were boiling and turning into a gas that way. All right? All right, and then vapor pressure. All right, so let's talk through this a little bit. Where are we? There we go. All right, and let's just kind of read through this. If a liquid is placed in a sealed container, molecules of the liquid begin to evaporate in the vapor space in the container. So they start to evaporate into here, okay? And that's kind of like an equilibrium type thing. There's a lot of water down here, not a lot of water up here, and they kind of the water kind of wants to spread out as much as it can inside that container to maximize its entropy, okay? And we'll continue to talk about that in the future, all right? The density of the molecules in the vapor state is high enough that the rate of molecules transitioning into the vapor state equals the rate of molecules transitioning back into the liquid state. So you've got this cycle going on. So you've got the same amount of liquid of water molecules up here in the clear airspace above the actual liquid surface, but they're always different. Okay, so they're rotating in and out. So this guy might be zipping this way, and boom, the hydrogen bonds get him, and so he's sucked back in. And he brings with him a little bit of thermal energy. So, and then, boom, this guy gets free, so he's back up here. And that might vary a little bit, but not very much, okay? So what that is vapor pressure. The pressure at which this equilibrium is reached is called the vapor pressure. Okay? It's a measure of the rate of evaporation of a liquid and its volatility. Okay, so here's another definition. Volatility is the tendency of a liquid to become a vapor. More volatile substances have a higher vapor pressure. Okay, I don't know if you guys have ever mowed the lawn and opened the can of gasoline and had the sun shining through so that it casts a shadow that you can see. You can clearly see gas coming out of there. Well, of course, gasoline is a mixture of a whole bunch of different hydrocarbons, and they actually put hydrocarbons in there that aren't really useful for burning in your engine, so that they will take up that vapor space and vent off when you open the container, so that you don't lose the stuff that you actually need to burn in your engine. Okay, so it's pretty crazy. And you just need to know at this point, I think we'll talk about partial vapor pressures a little later. Again, I don't know this whole book very well, so that might be true, or we might not get to it. I'm not sure. So strongly dependent on temperature. Okay, and look at water right here. Okay, so follow your finger here. Let's just go to immediately an interesting thing. Okay, so we come to 100 degrees C, which of course is what? That's the boiling point of water. Well, let's look and see what that is. Bring that back over here. So 700 is right here. 750 is right here. Okay. And so 760 is where that reaches, where 100 takes you. Okay. Well, what's interesting about that? Well, that is atmospheric pressure. Okay, 760 torr, normal atmospheric pressure. So, what do we take away from that? The vapor pressure, when it equals the surrounding atmosphere pressure, whatever that is, okay, that liquid boils. Okay, and we're not talking about the weird situations where it's like we're in space and the pressure's so low it goes straight to a solid or straight to a gas from a solid. We're not talking about any of that. Okay, we're talking about in everyday deals when the vapor pressure equals the atmospheric pressure, it starts to boil. Okay, just that's a fact that we need to know. So let's take note of that. Perhaps actually write that down. Okay, so how could we say that? We could say when vapor pressure equals atmospheric pressure, the liquid boils. Okay, now what does that mean? That means like we talked about Denver. So this is another way to discuss it. So if Denver is down here at 600 torr, we can come over here and we can see what the boiling point will be. Right here, it's probably 95. Okay, so that's probably close to what Denver's atmospheric pressure actually is. Okay, super easy to use. You just need to know this fact. Okay, that is how that term is defined. Okay. Oh, look, they even talk about Colorado over here. 502 torr. But you guys knew that because you read the chapter, and I didn't get all the way to the end there. Okay. All right. So now with the remaining 5 or 10 minutes, let's work through some problems, talking as we go, so that we can pull out the lessons, so that you guys can solve stuff on your own and not feel like he did all the easy ones, and now we're left with the hard ones, just like always. I always felt that way in chemistry and physics. All right. So let's talk through example 8.1. All right, so usually when I'm solving a problem, okay, I want to always write my equation because that is going to be my guiding principle there, okay? And remember that this is not, that delta is not separate. Ugh! Focus, people, focus. All right, that delta is not a separate thing. It goes with the t. It's the change in t. Okay? So anytime you're working with a substance, you'll have to be given this value. Okay? It'll always be given. Okay? I will not ask you to memorize that. That is a pointless thing. I might ask you at some point to know that 4.186 joules per gram degree C is the specific heat. So 1 gram of water, 1 degree C, takes 4.186 joules, which is also, what did we say that was? That's also a calorie. Okay, you need to store that away somewhere. I'm not going to ask you to memorize that. We'll hit that again in physics. Okay. All right, so let's look at 8.1 there. Determine the quantity of heat that must be added to 75 grams of water to heat it from 22C to 35C. All right, so again, we seem to be struggling as a class sort of generally on problem solving. Okay, so let's talk through what are some tips, what are some ways to organize your thoughts, because ultimately that's the issue. I don't think it's a math problem because you guys all have basic calculators, and you know when to have multiplication or division. Okay, so you need to be organizing your thoughts and converting a paragraph into a problem. The ACT is going to test you on this, as will the rest of chemistry and the rest of physics and college and yada, yada, yada. Okay, it's a critical thinking skill. All right, so what do we need? We're determining the quantity of heat that must be added. Okay, so right off the bat, we know Q is equal to question mark. Okay, and I don't have to see all this. Okay, I do want to. I'll show you what I do want to at least see. Okay. All right, and so then C. Does it say anything about C? No, it doesn't. Then we just must have to look it up. Okay, and what are we doing? We're adding heat to water, not doing steam or ice, so water. So we know that it's 0.0752 kilojoules per mole degrees. Well, we don't say degrees, but Kelvin. Okay, and again, that's the same unit. That a Kelvin degree is the same size as a Celsius degree. Okay. So this is the same number if we're using C or K. Either one's fine. All right. What else do we know? We need to know the number of moles. We don't know that yet, so we're given grams, so that doesn't help us. Don't plug that in, okay? Make sure you remember we're only talking about moles here, okay? And that's why that's another little tip is always write your units, guys. You're much less likely to plug it in wrong if you write 75 grams and then you notice that you're multiplying times something that's got mole in the bottom. You're like, good thing I wrote the units because I need to convert this to moles. Okay, so we'll get that in a second. What else do we need to know? We need to know delta T. And what's that? Pretty simple. We say final minus initial. What's our final? Is 35 minus 22. And what's that? 13 degrees C or 13K. They're the same, remember? All right, so for our N, what do we need to do? Number of moles, we need to go grams to moles. Okay, which reminds me, get me test corrections if you haven't. I need those by the end of the week, okay? All right, so grams to moles. What are we given? We're given 75 grams of H2O. And we know that 1 mole of H2O is what? 16, 17, 18. So 18 grams H2O. Okay, and a super precise grams per mole value is not what we're going for here. Okay, so 1 decimal place is fine, or if it's, excuse me, if it's 0.99994, just round it up to the 0 and drop the 0. Okay, guys, we're here to do the conversions. We're not here to nitpick that to death. Okay? So we see from the book there that that's how we end up with the 4.162 moles of H2O. Okay, that goes here. 4.162 moles of H2O. Okay, and I'm sorry if this is super slow for some of y'all, but trust me, some of your classmates, this is helping them. Okay, man. All right, so what do we have? Q is equal to C N delta T. All right, here's the step that I at least need to see on your quizzes and tests. Okay, I need to see this. C, we know it's 0.0752 kilojoules per mole. Okay. Number of moles, 4.162 moles. You could write H2 under there if you're being super careful, okay? And then our change in temperature is 13 degrees C or K. Doesn't matter. And then we literally just multiply, boom, 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 and we get 4.69 kilojoules. Okay, so note, we're in kilojoules. No, at no point do we go to joules, okay? So if you write 4690, you bet that's what you better write, okay? 4690 joules. That would be correct, okay? Do not write just joules. I will count off a point, okay? Because that's off by a factor of 1,000. It seems stupid. You did the math right, yada, yada, but you weren't careful, okay? All right, so let's do one from the other. And this could be asked 1,000 different ways, okay? I could give you a volume of water, and you'd need to know that density is equal to mass over volume, okay? And get to a mass, and that would probably be in grams. Then you go to moles. I could give you the moles. I could ask you how many kilojoules. I could ask you how many calories. Okay, and if I was asking you calories, I'd give you that number there. All right, I'm never going to try and trick you guys as just did you memorize a value, unless you've got to know that value. Okay, and I might ask you to do some conversions between kilojoules, megajoules, millijoules, something like that. So make sure you're looking back at those prefixes so you're fluent in those. Okay, those are skills that you're going to need to keep brushed up on all through. All right, and so really fast, we'll work the second one, and if you guys are out of time, feel free to watch this at home. Just pause me and y'all be done. Watch this at home. Oh, and before I forget, you guys I'm going to send out a homework probably tomorrow morning with questions from the XKCD. I'll send you the link and the homework, and I'll update the homework link to have a place to turn that in. It has a lot to do with the heat of vaporization, heat of fusion, all of that stuff. And it's super interesting and interesting thought experiment, which is why I really like reading his comics. All right, very quickly, we want to know if we have 5.75 moles water, how much heat must be added to vaporize it. Okay, how do we get there? All right, Q, N, heat of vaporization. Pretty straightforward here. How many moles? He gives it to you. Obviously, we could ask you to convert those. And then heat of vaporization just comes from your book at the top of 218, and it's 40.7 kilojoules per mole. And then we just multiply those together, and we get 234 kilojoules. Okay? Really, really straightforward calculations, but if you're not familiar with the terms, that could be a little difficult. Okay? All right, great. Start preparing in your heart of hearts for quiz on Chapter 8. Start to internalize what's going on. Start to think about themes in this chapter. Work your homework. Work the XKCD homework. And let me know if you got any questions. We have Monday, or I have Monday off, and you guys are working at home. So really try to make an effort Grab a ride if you can. If that time doesn't work because you can't catch a ride, let me or somebody else know. I will try to make sure everybody can get to that work session. It'll be worth it. We will go over all of Chapter 8, maybe get into a little bit of 9 so we can have some of that discussion with some of the concepts. But then we're also going to start looking forward to a lab report. Yeehaw! I know you guys are excited about that, almost as excited as I am to grade them. All right, so great. Looking forward to all that. Busy week coming up. Push through. The weekend's almost here. Work hard today and tomorrow, and have a good weekend.